Welcome back to educator.com. This is a continuation of linear algebra. Today we're going to be talking about vectors in the plane. So the plane is also represented as something called R2, which just means the real number squared. Basically you have the x-axis, which is the real numbers, and we just take a copy of the real numbers and we make it perpendicular, which is why we call it R2. By that analogy, normal space would be called R3, and n space is called Rn, r raised to the n power. Okay, let's go ahead and get started. Okay. In math and science, we talk about two types of quantities. One is a scalar, which is just a fancy word for a number, and the other is something called a vector. And in case you're wondering why it is that we actually differentiate, why would we even need something like a vector, what I'd like to tell my students is think of a pushing analogy. If somebody comes, let's say, in front of you and pushes you with a certain force, let's just say it's 100 newtons of force, that's a number. Well, you end up going backward in one direction. So let's say you're standing over here. If they push you this way, you're moving, you're going to end up being pushed that way. Let's say somebody comes from the other direction and pushes you in that direction, well, you end up moving that way. As it turns out, you end up in different places. You end up moving in different directions, but they're both pushing you with the same force. So there is a difference because this is not the same motion. So as it turns out in the real world, we need something more than just a number. A particular situation needs to have, certain situations, not all of them, need to have some other quality associated with them, and that quality is a direction. So if I say I'm going to push you with 100 newtons of force in this direction, that is we call it a vector having a length of 100, what we call a magnitude, in that direction. If it were the other way, well, we say it's a vector whose magnitude is still 100, but it's in this direction, and these are two very different vectors because they have different directions even though their magnitude is the same. So that's sort of a qualitative description of what a vector is. Okay, let's go ahead and talk about a reference frame for vectors. So we take as our reference frame the standard xy coordinate plane, the Cartesian plane, and to the right of the x is positive, and up on the y-axis is positive, negative, negative, nothing that you don't already know. Okay. Now, if I start at the origin and if I draw, well, let's not draw it first. Let me just pick a point. So I have this point. Let's say the point is 2, 4. Well, yes, it's true. It represents a point in space. But if I start from the origin and put the tail of an arrow there, and if I go and put the head of the arrow something like that, notice I've actually now given you an explicit direction from a particular point, origin. Well, since this Cartesian coordinate plane is our frame of reference, the origin will be our ultimate point of reference. So now I have an arrow associated with this, this coordinate here, 2, 4. Well, this coordinate is called a vector, and this arrow is also called a vector. They're just two different representations of it. So if I call this vector u, I can certainly represent it as 2, 4. And another representation of it that I'll also see is I'll write it as a column matrix instead of I'll write it like this, 2, 4. So notice this is 2 rows in 1 column. And remember, anything that has either 1 row or 1 column, we called it a vector. So now we can see why we can associate this idea of a vector with a matrix. We don't necessarily have to have this coordinate with a comma in between. We can just represent a vector as the point 2, 4. And again, you're also welcome to write it as a row vector 2, 4, not necessarily with the coordinate. I mean, the only difference being that little comma there. So this is still saying move 2 in the x direction, 4 in the y direction, 2 in the x direction, 4 in the y direction. And now we've introduced this other notion of it actually being an arrow from the origin to this particular point. So with this arrow, now we have a physical something, And now there's something else that we can associate with it. We can associate a length with this arrow because it has a particular length, and we can associate an angle from a reference line. Well, we take our reference line as the x-axis and we measure all angles in counterclockwise direction. So that would be considered a positive angle, and if I go this way, this would be considered a negative angle. If I go all the way around once, that's 360 degrees. If I go around twice, that is 720 degrees. 2 times 360? Yes, it's 720. So even though we end up in the same place, the angle measure is actually different. So again, counterclockwise, positive angle, clockwise, negative angle. X-axis is our reference line. The origin is our reference point. Okay, let's define a couple of things. So if we have a vector, let's just take a generic vector, u, and again, vectors have that little arrow on top of it, and I'll do it as a column this time. I'll often do both, and it's not really a problem. Later on, when we get into certain aspects of linear algebra, it's going to be important on how we actually use a vector, whether we do it as a column or a row, but for right now, it's not really much of a problem. So we define the magnitude. The symbol for the magnitude is, So u is our vector. We have the symbol for the vector, and we put 2 double lines around it. That's the magnitude, and that's just the length. Well, you know that if this is our vector, and let me actually draw it again over here, so make it a little more clear. Well, if I have this particular thing, and here is the point x, y, well, you know that we've moved to the right x units, and we've moved up y units, so this is y and this is x. Well, the Pythagorean theorem tells us that x squared plus y squared equals this length squared, so we define the magnitude as x squared plus y squared under the radical sign. That gives us the length of the vector, or the magnitude. All these fancy words. Now, we can also define this angle. So if we call this angle theta, well, we have y, we have x. The relationship between theta is tangent. So if I have the tangent of theta is equal to y over x, well, that implies that the angle theta itself is going to be the arctangent, or inverse tangent of what, these little lines, I don't want them to get in the way here of what we do, y divided by x. So when you're given a vector in this form, you can find out the length, and you can find out the angle that it makes with the positive x-axis. And remember, again, we're measuring that way. Okay? Okay, let's do an example here. So let's say I have the vector is 3, 7. Okay, so 3 in the x direction, 7 in the y direction. It's in the first quadrant. They're both positive. So the magnitude of u equals 3 squared plus 7 squared under the radical sign. 9 plus 49 equals 58. Radical 58. That is our magnitude. It is that long. And again, you'll find that when I come up with these numbers that are irrational under the square root sign, I often don't simplify. I just leave them like that. It's not a problem at all. Simplification, oftentimes, believe it or not, things like reduction and simplification, I think it often obscures the mathematics. Once you get a particular number, you're more than welcome to leave it like that. The angle is, we said it's the arctangent of y over x, so 7 over 3. And we end up with 66.8 degrees. Now notice, we haven't drawn anything here. Here we're talking about a physical object. We're talking about an angle, which is a geometric notion, and we've expressed it in degrees. You can express it in radians if you like. If you remember 180 degrees is pi radians, 3.14. You're welcome to do it either way. It's not a problem. We have this geometric notion. We have a point. It represents an arrow, and yet you notice we haven't drawn any pictures here. Now, you can certainly deal algebraically with vectors. It's not a problem. It's one of the reasons why we're doing it, linear algebra. Ultimately, we want to take a geometric notion and bring it into the realm of algebra, so we give it a firmer foundation than just drawing pictures. But pictures are a big help, and you want to make sure that you know what it is that you're dealing with. So we know that we're dealing with something in this quadrant, so when we get a number like 66.8 degrees, it actually makes sense. 3 this way, 7 this way. It actually should have been a little steeper, I apologize. But again, we want our numbers to make sense. So this is the number that is 8 degrees. And again, we're measuring it from the positive x-axis in that direction. Okay, let's do another example. Let's take a vector. Let's actually draw this one out first. Yeah, let's draw it out over here. So I'm going to have one of my vectors, shall I give them names? I'll call one of them T. How's that for tail? That's going to be 3, 2. This time I wrote it as a row vector. And this other one I'll call H for head, as in the arrowhead. And let's put this one at 7, 4. Okay, so 3, 2, oops, 3 minus 2 actually. So we'll go 1, 2, 3, 1, 2. That's tail, that's one thing. And the head is at 7, 4. 4, 5, 6, 7. And we go up 1, 2, 3, 4. And we are over here. So we have this vector right here. Now, notice this vector didn't begin at the origin. It's not a problem. Any vector that we can move it to the origin. So when we actually try to find, well, think of it this way. If we just move this vector over to the origin, it's going to end up being something like this. So as it turns out, any vector in the plane, whether it begins at the origin or not, is in some sense equivalent to a vector that actually begins at the origin. When we actually solve for the magnitude and the angle theta, we're just going to be dealing the same way we did before. We just take the difference between these two, the difference from the head to the tail. So in this particular case, our x value, in other words, this distance, is just the difference between the x values here and here. And our y value for the vector is the difference between the y values here and here. So let's find our x. It's equal to 7 minus 3. Always do the head minus the tail. Equals 4. And our y is equal to 4 minus a minus 2, which is 6. 4 minus a minus 2, which is 6. So what we have is this thing here, which doesn't begin at the origin, is equivalent to a vector that does begin at the origin that has, well, whose algebraic representation is 4, 6. So this vector is the 4, 6 vector. Well, so is this, except it doesn't start at the origin. That's why it's represented by 2 different points. So for all practical purposes, we can just deal with this one. They are equivalent. Okay, so let's do our, let's give this vector a name. Let's just call it S. So the magnitude of S, again with double lines, is equal to 4 squared plus 6 squared under the radical sign. 16 plus 36 is 52, I hope, if my arithmetic is correct. I often make arithmetic mistakes. And again, there's always going to be somebody there to check your arithmetic. There won't always be somebody there to check your mathematics. If you have to make a choice, mathematics comes first, not arithmetic. And our theta is equal to the inverse tangent of y over x, 6 over 4. You don't have to reduce. 56.3 degrees. That is this angle, which is the same as this angle because they're equivalent. not a problem. So again, when you're dealing with a vector that's been expressed with a head and a tail somewhere else except at the origin, you just treat it the same way. You just take the coordinate for the head minus the tail, coordinate for the head minus the tail, and you end up with a vector as if it is starting at the origin. Okay, let's do one more example here. This time we'll do, our vector is -6, -3. So again, picture is worth 1,000 words. We use pictures to help us understand what's going on. Pictures are not proofs. Algebra is a proof. So -6, -3, we're somewhere here. So we're looking at something like that. So just so we know what we're dealing with something in the third quadrant. So when we get our numbers, we want to make sure that the numbers match our geometric intuition, the picture. So let's take the magnitude of u. Well, it is -6 squared, which is 36, -3 squared, which is 9, all under the radical sign, which gives us a radical 45, if I am not mistaken. And our angle theta, here's where it's going to get interesting. The inverse tangent, and I apologize, I'm a little older, so I was actually taught as arctangent, but inverse tangent is fine. Y over x minus 3 over -6. When you enter this into a calculator, here's what you're going to get. 26.5 degrees. Okay, 26.5 degrees, just on the surface that doesn't make sense. We're in the third quadrant. We said that angles are measured from the positive x-axis over to that way. So I know that my angle has to be more than 180 degrees, less than 270 degrees. 26.5 doesn't really jive with that. Here's what's going on. If you remember from your trigonometry, whenever you take the inverse function, remember the graph of the tangent function? Well, actually, let's not worry about the graph. Let me just say, whenever you use your calculator, the value that it's going to give you for your angle is going to be an angle between -90 and +90, okay? Because the period of the tangent function is pi. So what this value represents, remember you're doing a tangent, so if you drop a perpendicular down to the x-axis, and it's always down to the x-axis, you never drop a perpendicular to the y-axis, this angle right here is what is 26.5. Remember, you're taking the arctangent of a distance, okay? -3 over -6. Well, here is your -3, here is your -6. It's just a distance over a distance. That's what the calculator is calculating. So for all practical purposes, it's acting as if the angle is somewhere here. That's why it's important to know where you are in the third quadrant. So now that and when we formally decide to measure this angle, we take the 180 plus the 26.5. So our actual theta is not 26.5, but based on our standard of this being our reference line, this is 26.5. From here, the formal theta is 180 plus the 26.5, which is 206.5. Positive. Okay, so we need to differentiate that. So there's a couple of things that we need to be aware of, which is pretty characteristic if you remember from working with trigonometry and angles. You have to be aware of which quadrant you're working in, and you also have to be aware of the signs of the trigonometric functions because the cosine is positive in the fourth quadrant, the sine is positive in this quadrant, and the tangent is positive in this quadrant. So we need the picture to help us to make sense of the numbers, okay? Okay. Let's see what we've got. Vector addition and scalar multiplication. Okay, so now that we have these things called vectors, we need to do things with them, and we can multiply them by scalars, and we can actually add vectors together. kind of the same way as numbers. Let's see what we have. Vector addition. We will let u equal, let's do u1, u2, and the vector v equals v1, v2. These are just the x and y components of this vector. Notice there are no arrows over them. Then we define the sum u plus v. Well, all you do is you add them component-wise. You add the x components of u with the x component of v, so it's u1 plus v1. And then in this case, you know what? I think I'm going to go ahead and put commas just to, and then you have u2 plus v2. We can also write it as, it's equivalent to u1 plus v1, u2 plus v2. This is the column representation. So all I've done is I've added my x components, added my y components, and now I have a new vector, which is u plus v. Let's talk about what this looks like geometrically. Okay, I'm going to put my u vector right there, and I'm going to put my v vector. I'll make it kind of short. Okay, don't want to run out of room. All this means is that do u, then do v. In other words, u is here, and then just do v. Well, v is a vector that goes in this direction and is that long, so just lay it on top of that. And you end up at that point. Well, as it turns out, as you remember, that point forms a parallelogram. That is the end. That's your beginning point. This is your ending point. So this vector, once you put the head there, this vector is our u plus v vector. So again, all we've done is we've done u first, and then we've done v. If you add 3 vectors, 4 vectors, 5 vectors, you just keep adding them and moving along, and where you end up, that's where the head of the final vector goes, and they all begin at the origin. So this is u plus v. Okay. Let's also do u minus v. Now, u minus v, well, there's no such thing as vector subtraction, but really what you're doing is u plus the negative of v. Well, the negative of v is just v, the same length, in the opposite direction. So this would be minus v. So now when we do u minus v, that means do u first, and then go v distance in the opposite direction. So we do u first, and then we go, well, v goes this way, so negative v is this way, so we go in the opposite direction. We go down that way. And we end here. That vector is u minus v. And you treat it the same way. If it's u minus v, well, it's this entry minus this entry. That forms the x-coordinate. This entry minus this entry. That forms that coordinate. And again, all you're doing is you're going along the vector. U plus v is do u first, then do v. Wherever you end up, that's where the head of the final arrow is concerned. So this is the vector u plus v. This is the vector u minus v. This is the original u. This is the original v. This is the minus v. Okay? Okay, now let's talk about scalar multiplication. Okay, once again, we will let u equal, let's just say xy. We can also write it as xy, so column matrix. So let u equal that, and a is a scalar, just a number. Then a A times u is equal to, well, A times x, A times y, or A times x, ay, written as a column. All I'm doing is taking the scalar a and multiplying it by every entry in the actual vector itself. What this means geometrically is the following. If this is my vector u, well, whenever I multiply by a constant, all I'm doing is expanding it. If the constant is greater than 1, I'm shrinking it if it is less than 1, and I'm pushing it in the opposite direction if it is negative. So if I have this vector, let's say it's xy, and if I multiply it by 5, that means I take that vector and I increase its length by 5. That means I've increased this x value by 5, I've increased the y value by 5. If I multiply by 1/5, I shrink it down by 1/5. If I multiply it by -5, that means it is a length of 5, but in the opposite direction. That's all that's happening pictorially, geometrically. Okay. Let's see what we've got. So let's take u is equal to 6 and minus 9. So 6 minus 9 would put it in the fourth quadrant. No, yes, 6, yes, fourth quadrant. And v is equal to 3, 4, which would put it in the first quadrant. So let's do u plus v. That's equal to, I'm going to write this as a column matrix. So 6 plus 3 is 9. Okay. And -9 plus 4. 6 plus 3 is 9. -9 plus 4 is -5. So our u plus v is that vector. How about u minus v? U minus v. Well, we do 6 minus 3, and we do -9 minus 4. 6 minus 3 is 3. Minus 9 minus 4 is minus 13. Algebraic. Now let's see what this actually looks like geometrically, just to get a sense of what's going on. We want our intuition and our algebra to match. So 6 minus 9 puts me somewhere down, let's say down here. Okay, it's my u. And again, we don't have to be exact here. You're welcome to work on graph paper if you want. That's always nice. And 3, 4, 3, 4, maybe somewhere up here. Okay, so this is u, and this is v. U plus v means do u first, and then do v. That puts us right there. This is u plus v. 9 minus 5, 9 minus 5, yeah, seems about right. It should keep us in the fourth quadrant. How about u plus v? I'm sorry, u minus v. We have u, and then minus v, which is down this direction. It's actually off the page, so it's going to keep us at 3 minus 13. Yes, it looks pretty good. 3 minus 13, yes, it jives. It's exactly right. So it's going to be a vector that's going to be and a little further down. So yes, everything seems good. But again, when doing these, it's the algebra that matters. We use the pictures to help us understand what's happening in order to make sense of the algebra, not the other way around. Okay. Angle between two vectors. Okay, let's draw a picture here. Let's just take one vector randomly there and another vector randomly there. There is an angle between those vectors. Let's call that angle theta. Now notice this is not the same theta as the angle of one of the vectors, which is from the positive x-axis. This has a theta. This angle also has a theta, but we're talking about the angle actually in between them. And as it turns out, there is a beautiful formula that allows us to work with this. So let's say this is u, and let's say this is v. We have two vectors in the plane. As it turns out, the cosine of the angle between them, which we've called theta, is equal to the dot product of those two things, u dot v, over the product of the magnitudes of those two vectors. And again, theta in this case is going to be greater than 0, less than 180. So when you actually work this out, you're going to get some angle from 0 to 180. An angle being 0, that means the vectors are pointed in the same direction. The angle between them is 0. Angle is 180, that means you have vectors that angle is 180. So if it goes past that, well, the answer you're going to get is that angle, not that angle. Okay, that's all this means. So let's do an example. So if we have u is equal to, let's say, 2, 5, and v is equal to negative 3 and 6, well, let's do the dot product, u dot v, and you remember it's product of the x values plus the product of the y values down the line. So 2 times negative 3, negative 6, plus 5 times 6, plus 30. Negative 6 plus 30 equals 24. So that's our dot product. That's going to be our numerator. And now the magnitude of u is going to be 2 squared, which is 4, 5 squared, which is 25. All under the radical sign is radical 29. The magnitude of v is minus 3 squared is 9, 6 squared is 36. That is equal to 45. Yes, radical 45. Therefore, our cosine of theta, using our formula up here, is equal to 24 divided by radical 29 times radical 45, which is 0.664. And when I take the inverse cosine of that, okay, so theta, let me go over here. Theta equals the inverse cosine of 0.664. I get 48.4. Let me write this a little more clearly, my apologies. 48.4 degrees. So that tells me that if I have u 2, 5, that's in this quadrant, negative 3, 6, that's in the second quadrant, I'm dealing with an angle between them of 48.4 degrees. That's really, really nice to be able to be just given the vector values and to be able to extract some geometric property that is not necessarily implied by anything. These are just sort of numbers representing things, and yet here we are able to tell you what the angle between those vectors is. That's very, very extraordinary. Okay, let's see. If u is perpendicular to v at right angles, then of course theta is equal to 90 degrees. Well, what's the cosine of 90 degrees? 0. So that means that 0 is equal to, I used u and v here. Let me, u dot v over the magnitude of u times the magnitude of v. Well, I just multiply both sides by the magnitude of u and magnitude of v, and I end up with u dot v equals 0. There we go. So, as it turns out, if the two vectors are perpendicular to each other, the dot product is 0. If the dot product of two vectors is 0, they are perpendicular to each other. We don't say perpendicular, we actually use the word orthogonal. So, u and v are orthogonal if and only if equivalence u dot v equals 0. So if I'm given two vectors, I take the dot product. If they're equal to 0, I know that they're perpendicular. If I know that they're perpendicular, I know that the dot product is 0. And the reason we say orthogonal instead of perpendicular is when we move to higher dimensions, and when we actually move later on, for those of you that go on into mathematics, you'll speak of actual functions that are orthogonal, and it's defined in a similar way. This is the power of abstract mathematics, is we start with the things that we know, 2-space, 3-space, pictures that we can deal with, and we can generalize to all kinds of mathematical structures that share the same properties. So we need a more general language to deal with them. So we don't talk about perpendicular functions, we speak about orthogonal functions. And so we might as well start now and start dealing with orthogonal vectors. Okay. Well, let's do something else here. What if we had theta equals 0, and let's take u dot u. Okay. Well, the cosine of 0 is 1. So let's actually write out our formula. So cosine of theta, so the cosine of 0 degrees is equal to 1. Well, the cosine of theta is equal to, let's take u dot u, let's just dot it with itself, just put it into our definition for the angle between two vectors. So, in other words, I have u and I have u on top of it. The angle between them is 0. So let me see if I can extract some information from this. So the magnitude of u times the magnitude of u, okay, multiply through, and I end up with u dot u is equal to the magnitude of u, which is just a number, squared. And if I take the square root of both sides, I end up with the magnitude of u is equal to u dot u. So now I have another way of actually finding the magnitude. What I can do is I can just take u dotted by itself and then just take the square root of that number. So, very good. Okay. Let's talk about some properties of the dot product and unit vectors. Okay. These properties are going to be reasonably familiar because we have mentioned them before. So, u dot u is greater than 0 if u is not equal to 0, and u dot u is equal to 0 if and only if u is equal to 0. In other words, if u is not the 0 vector, if u is not the 0 vector, then the dot product is always going to give you a positive number. B, u dot v is equal to v dot u, so the dot product is commutative. C, u plus v dot w is equal to u dot w, notation, plus v dot w. In other words, the dot product itself is distributive. And the final one, c times u dot v is equal to, I could pull the u out, u dot c times v, or I can just pull the C out and do U dot V. Again, just some properties to manipulate vectors when you actually start to deal with them. Okay, we're moving along very nicely here. Let us define a unit vector. Unit vector is a vector whose length is 1. That's it. A vector whose length is 1. Okay? And if you're given, so let's just say, so let x be any vector, the unit vector, which I'll actually notate as x with a little unit written down below, is equal to 1 over the magnitude of x times the vector itself. In other words, I take the vector and I divide each entry of that vector by the magnitude of that vector. Think of it this way. If I have the number 15 and if I want to turn it into a 1, I divide it by itself, right? Yes, I just divide by 15 and I get a 1. It's a way of taking that number and converting it to a 1. Well, vector, we're also dealing with direction. So I can't divide by a vector that's not defined in mathematics, but I can divide by a number. So if I take the actual vector itself, all of the components, and if I divide each of the components, which are numbers, by the magnitude, which is a number, I essentially just scale it down by its magnitude. In other words, I turn it into a vector of length 1 in any direction, because we're talking about any vector. Okay. Let's see. We have two very important unit vectors. Okay. We have the vector in the x direction, which we symbolize as I, and we have the vector in the y direction, which we can symbolize as j. In other words, there is a unit vector, length 1, that way, that's called I, and there is this unit vector right here, and that's called j. Well, as it turns out, we can express any vector in the plane by a linear combination of these two. And what that means is the following. Let's say I have a vector x, and let's say it is, I'll write it in multiple forms, 7, 9, which is equivalent to 7, 9. I want to express this as a combination of these unit vectors. Well, the unit vector is just a vector 1. Well, if I multiply it by this value in the x direction, that means move in this direction, in the direction of the unit vector, that many units. So another expression for this would be 7 times the unit vector I, that means move 7 units in the direction of I, plus 9 units in the direction of j. And remember, these are vectors. Vector addition just means do this one first, then do this one. All this is saying is, well, you know that this is 7 in the x direction, 9 in the y direction. Well, this is saying 7 in the I direction, which is the x direction, and 9 in the j direction. So I've just sort of combined vector addition, scalar multiplication, and I've represented with these two very unit vectors, the I and the j, and any vector in here can be represented as a linear combination, and a linear combination just means a sum. That's 1, that's 2. Move 7 units to the right, move 9 units up. If I might have something like minus 6i, minus 3j, that means move 6 units in the opposite direction of I, that means this way, and move 3 units down in the j direction, that means this way. That puts us somewhere over here. Any vector in R2 can be represented by a linear combination of these two vectors. And you'll discover later, any vector in, let's say, 13 space. Well, I need 13 unit vectors, and I can represent any of those vectors by all the 13 little unit vectors in that particular coordinate frame. We'll talk about that a little bit later. Okay, let's finish off with an example here. Let's say we have the vector x, which is -2, -3. So that puts us in the fourth quadrant. Okay, so we want to find a unit vector in this direction. Okay, well, let's go ahead and find out what the magnitude of x is first. It's going to be -2 squared, 4, -3 squared, 9. Under the radical sign is equal to radical 13. So our unit vector in the direction of x is equal to 1 over radical 13 times -2, -3, which is equal to, we'll just multiply it through, -2 over rad 13 and -3 over rad 13. That is my new vector. Notice I have an x coordinate and a y coordinate. I've divided it by the magnitude of the vector itself. This vector has a length of 1. In other words, if I were to find the magnitude of this vector, I would do -2 over radical 13 squared plus -3 over radical 13 squared under the radical sign. I end up getting 1. That's the whole idea. Very, very important concept, the unit vector. And again, notice I've left this radical 13 in the denominator. It's not a problem. It's perfectly valid mathematics. Don't let anybody tell you otherwise. Thank you for joining us here at educator.com. We'll see you next time for linear algebra.